Hello, welcome back. So in this class we'll learn about superposition, interference and Young's double-slit experiment. So in the world of waves, an important concept is superposition. When two or more waves meet, they combine to form a new wave pattern, and this is called as a superposition. So the displacement of the wave adds up or subtract depending upon how they are meeting. So you can see this visuals where one wave is stationary and then second wave is moving it to the right. The resultant displacement is the vector sum. So in this example, if I see at this spot, the wave 1 has some positive displacement, wave 2 has zero displacement. So if I add them together, you get the displacement of the resultant wave. This is pretty easy. If the wave 1 has the negative displacement and wave 2 has a positive, so you do add up like the positive and negative. Similarly, you can take this. If I'm treating, let's say this is a positive 2 and this is a minus 3, then I'm going to say the net displacement will be positive 2 minus 3, which turns out to be minus 1. So the displacement of the resultant wave is going to be minus 1. It's just the vector sum of the displacement of the individual waves. So in order to see where the maxima and minima occur, we need to understand the interference pattern. Let's look at this. If S1 and S2 are the two identical sources that are emitting this sound waves, so if the two waves meet like this way, if the crest of one wave and then crest of another waves meet, having the same amplitude A and then A, then resultant amplitude will be the double of their individual displacement because they are identical waves. This is called as constructive interference. On the other hand, if the wave 1 having the amplitude A exact matches the amplitude of the other waves but in opposite direction, or we call it as out of phase, in that case the resultant displacement will be zero. That is called as destructive interference. That can be well understood if you see these two waves. So let's say these are the two waves which are traveling. So if you look at the position A of the wave 1 and like the various position of the wave 2, so when the wave A, like wave 1, meets like this, they're coinciding now. So the path difference between the point A and then B will be zero wavelength because they are coinciding. So A and then B are simply coinciding right now. So the difference in the point A and then B is null, zero wavelength, and hence these two waves meet one another like constructive interference. If you look at the position A and then B, then it's half a wavelength ahead. And at this point, if the waves meet like this, they'll create a destructive interference. They'll destroy one another. So resultant amplitude will be zero. Point A moves to the point D, then the space between B and then A is now one full wavelength apart. So I can say the path difference is one full wavelength apart. Or you can also say the angle difference between them is 360 degree or 2 pi radian. In this case, again waves will meet constructive. So every integral multiple 0, lambda, 1 lambda, 2 lambda, 3 lambda, waves are meeting constructively or in phase. So you'll get the constructive interference, while every half integral multiple, one and a half lambda, 2.5 lambda, the waves will go destructive interference. So this is the condition or the criteria which we need to write down, that if for constructive interference means the waves will add up more when the path difference is n lambda, where n will be integral multiple 0, 1, 2, 3, 4 and so on. While destructive interference, the wave will destroy one another if the path difference turns out to be n plus 1/2 lambda, where again n will be 0, 1, 2, 3, 4 and so on and so forth. So to understand the path difference better, let's look at this too. So if I take a point source S1 and S2, they are emitting the wave fronts. And if I take any in general point, let's call this point as this. Let's call this point as Z. So to reach the point Z, this, and from S2 also it will take certain amount of waves to reach the point Z. If you read that, like the S1 to Z, that distance can be covered as 1 wavelength, 2, and then 3 wavelength. So 3 wavelength is the distance. Similarly, S2 to Z, it is also like 1 wavelength, 2, and then 3 wavelength. So the path difference will be, you can take the mod value of S1Z minus S2Z, it comes out to be 0 lambda, and at such point, if the path difference is 0 lambda, you will get the constructive wavelength. That means the waves are overlapping like this, as we saw. Similarly, if I take any other point, let me just take you one more point. Here, if I take a point this, let's call it as X. So S1 to point X and S2 to point X. S1X, that distance gonna be 1.5 lambda this time, because it's in the middle of it. 1.5 lambda. And then distance to reach the point X, the S2 will take 0.5 lambda, and then whenever we see the path difference of 0.5 lambda or 1.5 lambda or 2.5 lambda, half integral multiple, you get the destructive interference. These are the two sources in this waves. So as you can see, exactly at the path difference of 0 lambda, a constructive interference, and half integral destructive interference. It's the same diagram. So that's what the Young's double slit experiment is. So exactly, I can write it over here. This is the point where the path difference is 0 lambda. This is the path difference 5 lambda, in 1 lambda, and so on and so forth. 0.5 lambda, 1 lambda, so on and so forth. What Young's did, instead of taking the two source light, he just took one source and let it pass through the two slit. Instead of taking two source, he took two slit number 1, slit number 2. So light from this generator passes through it with the wavelength lambda apart. So the space between them is a wavelength. From each slit, the waves will diffract and then diffract over here, and then they will interfere. So exactly at the center, again when the path difference is like 0 lambda, you will see the maxima position. Path difference of 0.5 lambda, you'll get the minima. 1 lambda, again maxima, and so on and so forth. Same goes on the other side as well. But if you notice, the intensity is decreasing over as you move further away from the central maxima. Intensity is decreasing because intensity of central maxima is really high compared to the first maximum. Purpose of Young's double slit experiment, the central maxima, these are called as fringes. This is the bright fringe, another bright fringe. The separation between the two bright spots is called as the fringe separation. So this is what the fringe separation, I'm going to call it as S. Then the distance between the two slit is called as slit separation, tiny d. The distance between slit and then screen, that's called as capital D. And then space between the two vertical lines over here, the wavefront, which call it as wavelength. So there is Thomas Young, who tried to calculate the wavelength using these terms. He said the fringe separation S, which is directly proportional to the wavelength, directly proportional to the separation between the slit and then screen. That's a capital D, the distance between slit and then screen. And then tiny d is the distance between the slits. By knowing this, you can actually determine the wavelength of that light. So Young's double slit experiment to determine wavelength of the light. If you make lambda as a subject, s into tiny d upon capital D. So using that, you can calculate the wavelength of that any waves. So one thing I would like to emphasize over here, that intensity pattern keeps on decreasing. Intensity patterns of that fringes keeps on decreasing as the waves move further away from the central maxima. The reason being is that this is the vertical perpendicular line, so the intensity, the distance will be smaller, and as you move further and further away from here, as you move further away from the source, the distance increases, and hence we know the intensity is inverse proportional to the distance square as well, the distance from the slit and then screen, because that's a non-perpendicular distance. The fringes will be equi-intense if the slit width is negligible. Width is extremely tiny. In that case, intensity will be, all of the intensity will be the same. So this is the property, because in that case the light will diffract the most. Comparison between this intensity versus distance graph compared to the second one is, the second one has a smaller or negligible slit width. In that case, intensity of the all maxima is gonna be the same as the central maxima. So I hope you understood this. See you in the next class. Thank you. That's it for today, folks.